CFD analysis of a Russian turbine versus an experimental design, Group 9. Mixing is a unit operation required in many industrial processes. Mixing processes are designed to blend two or more components in order to obtain a uniform mixture. This homogenization process is often connected with mass transfer, although heat transfer is also involved. This unit operation is carried out on agitated vessels, which typically contain one or more impellers on a shaft, sometimes baffle and other internal pieces such as draft tubes. Impellers geometry is of great interest as it substantially affects the efficiency of the agitation process in relation to the component mixed. Impellers are mainly divided according to the flow the streams generate. Axial flow impellers, which generate streamlines parallel to the shaft, and radial flow impellers, which generate them perpendicularly. The most employed one is Russian turbine. The project's main objective is to characterize a Russian turbine and an experimental design using CFD in order to determine their power number curve. There are many parameters that affect the efficiency of agitating process. Among them is the shape of the tank and impeller, the number, type, and size of the blades, the number of the baffles, etc. This provides great variability of the performance based on the overall design, and because of this, the main factor that we'll be studying in this case is the impeller's design. In recent years, the CFD tool has been implemented in order to observe the effects of change in these parameters and obtain better performance according to operating conditions and fluids. It was found that implementing flat blades with perforations and grooves increased the effectiveness in pumping in the deformation speed and decreased the required energy expenditure.
For a valid simulation, a proper mesh is first needed. In this case, this was created using a surface remeasure, which refines a surface mesh to obtain a better volume mesh. A polyhedral measure, which employs a tetrahedral mesh and optimizes it to obtain a balanced solution for complex geometries. And finally, a prism layer measure with 3 layers, to properly reproduce the fluid near the wall. Additionally, a mesh refinement was done on the impeller blades, customizing the minimum and target size in order to increase the number and quality of the cells there. As a final result, both meshes have almost 900,000 cells, although the percentage of cells in the rotating zone, specifically on the impeller, is higher for the designed impeller, as the geometry is of higher complexity. As for the physics, the most important models enabled were the three-dimensional, the implicit unsteady model in which the different properties of the fluid vary over time, segregated flow, which solves momentum equations for each dimension independently, constant density assumed all throughout the tank, shear stress transport kappa omega model, which uses a two-equation model for turbulent kinetic energy and specific dissipation rate. This approach effectively blends a kappa epsilon model in the far field with a kappa omega near the wall, curing the biggest drawback of the original standard kappa omega model to practical flow simulations. Two-layer all-white plus wall treatment was also used, providing valid boundary conditions near the wall. Finally, gravity acceleration is taken into account for buoyancy effects. It is important to mention that turbulence suppression was used too in order to mimic the effect of transition, and laminar models were used accordingly to the regime of flow for the proper lower Reynolds numbers. An almost identical average cell quality value of around 0.69 can be seen for the volume mesh of both geometries, which is in general really acceptable. It can also be seen that thanks to the mesh refinement done on the impeller blades, the cell quality does not decrease drastically in this region, which means a more accurate solution for the simulation.
As a starting point for the simulation, the rotation speed was calculated from the stipulated Reynolds number, using the viscosity, density, and impeller's diameter too. The latter is different between simulation, but as a factor of analysis will not be taken into account as the variation between them is around 1%. This rotational speed was assigned to the motion reference frame of the rotating zone to describe the impellers and shaft movement. As a general tendency, it can be seen that except for the power number, every other value increased with the growth of the Reynolds number and therefore the rotational speed. In addition, it is seen that the shear rate increased linearly, which is to be expected according to the literature as shown in the graph. Another presenter values, such as the torque and the power, show an approximate quadratic and cubic relation to the rotating speed, respectively in turbulent flow regime.
From the data obtained, a regression for the new impeller design was elaborated. Both this regression and the one provided as literature for the Rushton turbine were contrasted against the simulation data, calculating the root mean square error. As it can be seen, this value is higher for the Rushton regression, due to, it seems, the regression not properly approximating to the true power number for laminar regimes of flow. In addition, it is important to highlight that for this representation, the power numbers obtained for a Reynolds value of 1 were not shown, nor they were considered for the root mean square error, as the discrepancies can be a result of incorrect numerical solution in the simulation and were classified as outliers.
The behavior between the turbulent kinetic energy in both models for a Reynolds number of 1000 is similar. As a start, the lowest values can be observed on the proximity of the walls, including the shaft. This due to the no-slip condition established. It can be also seen that the higher values are obtained for the Rushton turbine, especially near the impeller, as a result of the geometry. The new design geometry lowers the amount of power supplied by the impeller. As a direct consequence, the energy transmitted to the fluid will also be lower. For a Reynolds number of 100,000, the same behavior can be observed, in which the highest values are obtained on the edge of the impeller blades. Nevertheless, further discussion in relation to the energy pattern shown previously cannot be described, as the total physical time employed for the simulation was significantly lower, due to the lower time step specification. However, the values are again higher for the Rushton turbine as a result of the higher power transmitted to the fluid. As it is to be expected, the highest values of velocity are obtained on the edge of the impeller blades, as the rotational speed is the same on it, but due to the distance from the center, the tip speed is higher. The no-slip condition can be also detailed from the velocity patterns, as the darkest tones of blue are located near the walls, including the shaft. Then again, the peak velocities are displayed on the edge of the impeller blades. In addition, here it is even more clearly seen that the Rushton turbines generates a higher displacement of the fluid as an obvious result of the surface area contacting in on the blades.
The main difference on the two animations observed lies on the displacement of the fluid as shown by the streamlines. For the new impeller's design, streamlines show a rather low length in comparison with the tracers seen on the Rushton turbine. This is a result of the perforations on the blades. As for the Rushton turbine, the flat surface produces an outward displacement, boosting the fluid towards lower mixing regions on the top. On the other hand, the perforated blades do not produce the same boost from the reduction of the surface area. As a first conclusion, it can be seen that the results match the literature survey. The power number for the new design was on average 45% lower on turbulent regime. Further study is encouraged in order to truly evaluate if the new design presents higher efficiency values for the mixing process. The disparity between the results and the theoretical values as shown by the root mean square error can be caused by multiple factors. For example, if a correlation for a lower range of Reynolds number was employed, the approximation could be improved.
Also, the model employed K omega SST could not be the most adequate for a fluid over the transition region, and even though the turbulence suppression model was selected, the software user guide indicates this is not a true transition model. As a final remark on the work produced, an analysis between simulations with a similar maximal physics time is proposed, which could allow the easier comparability on the results obtained in a regard of a more appropriate representation of what a real life study could account for.